The first law of thermodynamics states that the energy of the processes taking place in nature is conserved, but it does not tell us whether a process occurs in a given direction or in the opposite one. The first law only imposes a constraint on the energy balance of the thermodynamic processes. If the heat Q is exchanged between a system and its surroundings while a given work W is done on or by the system, we can compare the initial and final states of the system, that is the states before and after the thermodynamic process. Then the first law tells us that the change in the internal energy U of the system is equal to the sum of the heat Q and the work W. However, the first law does not determine the direction of this process. For example, if a ball falling from the given height has a collision with the ground which is not perfectly elastic, then the deformation of the ball produces a given amount of heat warming the ball and its surrounding. The law of conservation of energy states that the heat is equivalent with the energy given by the product of the mass of the ball, the gravitational acceleration and the height. The law of conservation of energy still holds in the reverse process, where the ball at rest on the ground absorbing some heat from its surroundings could ascend at the expense of cooling down the system. The exchange of heat in the collision between the bouncing ball and the ground can be determined, for example, by using a thermal camera detecting the increase of the temperature of the ball. Therefore, we talk about a thermodynamic process which we can reproduce all the time. However, its reverse process never happens. Another simple example is the Joule experiment, where a falling weight drives a paddle while stirring the water in a calorimeter, where the water can be warmed by a rotating paddle while immersed in the liquid. In the inverse process of the Joule experiment, the heat absorbed by the water would be converted to work driving the paddle wheel in the opposite direction and lifting the weight. Although we can perform the Joule experiment whenever we want, we never see that the weight is lifted at the expense of cooling the water. The thing that the reverse direction of these examples and many other thermodynamic processes in nature have in common is some equipment extracts heat from a heat bath, for example from the ground or from a liquid in a calorimeter, and produces a given amount of work equivalent with the heat, for example lift the ball or the weight, while no other change takes place in the system. Since the existence of such a device or engine does not contradict the first law of thermodynamics, it is not a perpetual motion machine or perpetuum mobile of the first kind. However, if such an engine operated on a cycle, it would still be very valuable, since it could convert the virtually inexhaustible amount of heat stored in oceans, the ground or the atmosphere into useful work. Then the engine capable of producing work in such a process was a perpetuum mobile of the second kind, as Wilhelm Ostwald stated in 1893. This fact is summarized in the second law of thermodynamics, stating that a perpetuum mobile of the second kind cannot exist. The original formulation of the second law is dated back to William Thomson, also known as Lord Kelvin, in 1851, which was reformulated by Max Planck in 1897. The Kelvin-Planck statement is the following. It is impossible to construct an engine that extracts heat from a heat reservoir and converts it into work without producing any change. Here the key phrase is without producing any change. A heat engine extracting the heat Q from a hot source and converting it into the useful work W' in a thermodynamic cycle, while the source always has the same temperature T throughout its operation cycle, is forbidden by the second law, if the complete transformation of energy from heat into work is the only final result of the cycle and there is no other effect. For example, a gas during its quasi-static isothermal expansion in a cylinder with a moving piston completely converts the heat extracted from a heat bath into work, but together with other changes. At the end of the process, the piston is located at a different position as a result of the increase in the volume of the gas. In order to restore its original volume, the isothermal expansion must be followed by another step in a thermodynamic cycle, for example the Carnot cycle. However, such a cycle uses another heat bath, a cold reservoir where some amount of the heat is dissipated. In other words, heat engines must exchange heat with two thermal reservoirs, a hot source and a cold sink, as seen in the figure where the heat engine extracts the heat Q1 from the hot source at a high temperature T1, produces the useful work W', and rejects the heat Q2' into the cold sink at a lower temperature T2. Another formulation of the second law of thermodynamics was introduced by Rudolf Clausius in 1850. His statement is equivalent to the Kelvin-Planck statement and also provides a criterion related to the direction of processes in nature. The second law of thermodynamics formulated by Clausius states that heat can never pass from a colder to a warmer body without some change connected therewith, occurring at the same time. In other words, heat never flows spontaneously from a colder body to a hotter body. We can compare this formulation with the Kelvin-Planck statement by rephrasing it the following form. It is impossible to construct an engine that operates in a cycle and produces no effect other than the transfer of heat from a cold reservoir to a hot reservoir. As in the case of the Kelvin-Planck statement, we see restrictions allowing only processes involving some change or other effect besides the heat transfer. It can be illustrated by the examples of refrigerators or heat pumps, where some work is done by the surroundings. In the case of a heat pump operating in a reversed Carnot cycle, the heat is extracted from a thermal reservoir with a lower temperature T2, called cold source, and transferred into another thermal reservoir with a higher temperature T1, called hot sink. On the one hand, external forces do work W' or minus W, and in the other hand, not only the heat minus Q2' is extracted from the colder heat bath and dumped in the warmer one, but some extra heat equivalent to the work done in the process is also absorbed in the hot reservoir. Therefore, the magnitude of the heat minus Q1 delivered to the warmer heat bath is greater than the magnitude of the heat minus Q2' extracted from the colder heat bath. We can also demonstrate the equivalence of the Kelvin-Planck statement and the Clausius statement by showing that if one statement is false, then it necessarily follows that the other statement is also false. In other words, the violation of either statement will result in violation of the other one. First, let us assume that the Clausius statement is false, and there is a heat pump which violates the Clausius statement by removing the heat minus Q2' from the cold reservoir at a temperature T2 to the hot bath at a temperature T1 without any work done on the system. That is, the heat Q1 rejected into the hot bath is equal to the heat Q2' extracted from the cold bath. Such an impossible arrangement is called Clausius violator. Now let us consider a heat engine operating between the same reservoirs at the temperatures T1 and T2. It extracts the heat Q3 from the hot source at the temperature T1, converts a part of this heat into work W', and discards the heat Q2' to the sink at the temperature T1. In this arrangement we used a heat engine that dumps the same amount of heat in the cold reservoir as the one removed from the reservoir by the heat pump. By applying the first law of thermodynamics, the heat Q3 extracted from the hot reservoir can be written as the sum of the heat Q2' dumped in the cold reservoir and the heat delta Q equivalent to the work W' done by the heat engine. In the combined system of the Clausius violator and the heat engine, the net heat removed from the hot reservoir is equal to delta Q, whereas the net heat transfer between the cold reservoir and the combined system is zero. As a result, the combined system can be considered as a heat engine which extracts the net heat delta Q from the hot reservoir and converts it into the useful work W', without rejecting any heat in the cold reservoir. But producing work with a single reservoir contradicts the Kelvin-Planck statement, that is, the combination of the Clausius violator and a heat engine is a Kelvin-Planck violator. In other words, if the Clausius statement is false, the Kelvin-Planck statement must also be false. Conversely, if the Kelvin-Planck statement is false, the Clausius statement must also be false. It can be seen immediately if we combine a heat pump with a Kelvin-Planck violator, where the work produced by the violator is the input work of the heat pump transferring heat from the cold reservoir to the hot reservoir. Then the combined system pumps the heat from the cold bath to the hot bath without any external work, and we obtain a Clausius violator. Therefore, the two forms of the second law of thermodynamics introduced by Kelvin, Planck and Clausius are completely equivalent. When we study the direction of thermodynamic processes, we can divide the processes into two groups, reversible and irreversible processes. We talk about a reversible process if a thermodynamic system evolved from an initial state to another state can be brought back into its initial state without causing any permanent change in its surroundings. Otherwise, the thermodynamic process is irreversible. A simple example for a reversible process is the single swing of a frictionless pendulum, that is a point mass m suspended from a string of the length L, where there is no loss of energy in the frictionless motion. Here the pendulum is initially displaced to one side by a small angle phi, and released from rest. Since its motion is frictionless, the pendulum will retain its initial displacement described by the angle phi after a single swing. We already mentioned the example of a ball bouncing back from a horizontal surface. We can also consider a ball dropped over the stretched rubber sheet from a given height h. If the collision of the ball with the stretched rubber sheet is perfectly elastic and the deformation of the rubber sheet is not permanent, then the bouncing ball can reach its original height h. This result indicates that the perfectly elastic collision is a reversible process. More generally, we can state that any mechanical process without friction or production of heat is a reversible process. In the case of heat production, we talk about thermodynamic processes. In thermodynamics, we also study quasi-static changes in the state of a system, and such processes, for example the Carnot cycle, can be considered reversible ones. We also mention some examples of irreversible thermodynamic processes. The first example of an irreversible process is the production of heat due to friction, that is the conversion of frictional work into heat. When a constant force F is exerted on a body such that it can slide over a surface and covers the distance s, the frictional work depending on the smoothness or roughness of the contact surfaces causes the molecules or atoms on the rubbing surfaces to move faster. That is, these particles gain more kinetic energy and some heat Q is released over the contact surfaces. In Joule's experiment, the work done by the gravitational field pulling the weight and rotating the paddle while immersed in water is also converted to heat in the calorimeter. In order to restore the initial state of the system without any other change, we need a device that was able to extract heat from the previously warmed water in the calorimeter, and transform it into work by lifting the weight without applying any external force. However, such a device would be a perpetuum mobile of the second kind forbidden by the second law. Another example for irreversible processes is the adiabatic expansion of gas in vacuum without any work done on the system by external forces. This process was studied in the Gay-Lussac experiment, and its irreversibility can be shown as follows. In this figure, the gas is initially in the part A of a cylinder sealed by a piston. During the adiabatic expansion of the gas, it moves the piston and fills the part B in the cylinder without exchanging heat with its surroundings. If a spring pushes the piston into its initial position, the gas will be compressed while restoring its initial volume in the part A of the cylinder. But during its compression, the gas warms up and the spring does work at the expense of its potential energy. These two effects can only be eliminated by applying such a device that was able to cause for the piston to return to its initial position at the expense of cooling the gas down. Again, such a device would be a perpetuum mobile of the second kind forbidden by the second law. It can be shown that diffusion and thermal conduction are also irreversible processes. Friction and other dissipative processes cannot be eliminated completely, and strictly speaking all the processes in nature are irreversible. Reversible processes are their ideal limiting cases, and therefore invaluable in thought experiments.